All right, so let's take a look at the pre-lab questions. Now, it's a little different from what we're actually going to be doing because we're burning food, but if we were burning candle wax underneath a can of water, we could also calculate the heat of combustion for a candle. It's much more interesting to do it with food, though, because we can convert it easily into calories and think about it in terms of the food that we eat. So first it says, write out the combustion reaction for wax. C25H52, we know combustion reactions are always plus oxygen, and the products are always carbon dioxide and water. Let's use the Cho method to balance this. C25, 25 C's. H52, 26 times 2 is 52. Now for the oxygens, we've got 50 oxygens here, plus another 26 oxygens makes 76 oxygens, and half of 76 is 38. So now we've got 76 oxygens on both sides. So the coefficients are 1, 38, 25, and 26. Oops. Going all over the place. All right, next one. It says you're going to be determining how much energy per mole of wax burned. And it says, what about these scenarios? Calculate the kilojoules per mole. Whenever you see the word per, think divide. So for the first one, 78 kilojoules per 0.25 moles. What is that in kilojoules per 1 mole? It's 312. I just divided that in my calculator. Now it's making us do a little bit more work in letter B. It says you've got 40 grams of butane, C4H10, and it releases 127 kilojoules. Ultimately, we're calculating kilojoules per mole. But first, how many moles of butane do we have? So we need to add up the molar mass of C4H10 to figure out how much 1 mole of C4H10 weighs. And the molar mass adds up to be 58.1 grams of C4H10 for 1 mole. So 40 grams, we don't even have 1 mole. We've got 0.69 moles. So what's the heat of combustion? 127 kilojoules per 0.69 moles comes out to be 184.06 kilojoules per mole. It's kind of building these levels now. Letter C. What if you're burning ethanol underneath some water and it raises 250 grams of water 37 degrees Celsius? This is exactly like what you're doing in your lab, burning food only instead of ethanol. So we're taking the mass of the water times the specific heat for water times the change in temperature. So here it's 250 grams, and water requires 4.18 joules per gram to go 1 degree Celsius, and we're going 37 degrees Celsius higher. So this comes out to be 38,665 joules. So if that was 0.5 moles burning, what is this in kilojoules per mole? Well, first I have to divide by 1,000 to get it into kilojoules. So 38,665 divided by 1,000, that's 38.665 kilojoules. Divided by 0.5 moles, that comes out to be let's see here, 77.3 kilojoules per mole. I had to punch that into my calculator. All right, last one. Instead of giving you moles, it gives you how many grams you're burning. So in our lab, we're not going to have to do kilojoules per mole. We're going to get to keep it in kilojoules per gram, because when you eat something like Cheetos, it doesn't give you how many calories per mole. It tells you how many calories per gram for the serving size. All right, so first, what are we doing here? We are burning methane underneath some water, and we are burning 5 grams of methane. Methane is Ch4, it says. Okay, so first let's figure out the molar mass of Ch4. 1 carbon, 4 hydrogens, that's 16 grams. So if we are only burning 5 grams, that comes out to be 0.31 moles of methane that we're burning. Okay, what energy did the water change by? So we need Q equals MCAT. The mass of the water is 340 grams times the specific heat for water times how much the temperature changed. It went up from 22 to 68. So I need to do 68 minus 22. That is 46 degrees Celsius. Multiply that together, comes out to be 65,375.2 joules. So finally I'm going to put this all together and get kilojoules per mole. So first I need to do 65,375.2 joules divided by 1,000. That's 65.375 kilojoules divided by the 0.31 moles that I got in the first part of this question. Final answer, 209.2 kilojoules per mole is how much energy methane gives off. All right, there you go.